Okay, so we are ready to start our next unit. This is Unit 12 on thermochemistry. This is Strand 11. So take a minute and set up your paper. You can pause this and set up your paper, and then you can start this back up. So this is Strand 11, and Strand 11 basically says that you're going to understand energy changes that occur in chemical reactions. Understand energy changes. Remember that capital E is typically how we abbreviate energy. So understand energy changes that occur in chemical reactions. And we're going to start off with 11A. And 11A, and we've talked about this a lot before too, describe energy in its forms including kinetic energy, potential energy, chemical energy, and thermal energy. So describe energy and its forms including kinetic energy, potential energy, let's put this over here, chemical energy, and thermal energy. And I'll remind you what those little things are abbreviations of as we go through here. So the first thing you need here, and I'm going to draw my line right across here because apparently I forgot to do that. The first thing you need, though, is just a basic understanding of what is energy. You know, everything in the universe is made of either matter or energy. Well, matter is anything that has mass and takes up space. So energy is defined as the ability to do work. Okay, and what do we define as work? Pretty much work has this really broad definition in science. You know, it's not like, you know, what your mom's definition of work is where, you know, clean your room. That's what work is. In science, we have a definition of basically, and I'm going to make it really simplistic, you can move stuff. When stuff is moving, when you get it to move from one position to another, that means you've done some work. So if you blink your eyelids, you've moved your eyelids across a distance, technically that's work. Okay? So energy means that you have the ability to do this. You've got some form of energy that you can save or keep or use immediately to move something in some form or another. So there are several types of energy. And the first one, as we talked up here in the TEK, the first one is KE, kinetic energy. And this is energy of motion. This is actually moving stuff. When something is moving, we call it kinetic energy, energy of motion. And there's an equation for that. We've talked about this before too. In the equation for kinetic energy equals 1/2 times the mass times the velocity squared. And we'll talk about that too. I think I have a paper in your packet where we can talk about that. So kinetic energy is that energy of motion here. Within that kinetic energy, we really can talk about thermal energy. So if you go up here to your TEK, kinetic energy, within that we can really talk about thermal energy. So thermal energy, and you guys all know what the word thermal means, or therm, that prefix, means heat, right? So thermal energy is heat energy. And heat energy really talks about the motion of the molecules. Or particles if they're not in molecule form. And if you remember on our last unit when we talked about gases and the kinetic theory of gases, particles are in constant motion, right? So we're talking about that now. And also when we did the stuff with gases, I told you guys that every time we used equations in the gases, we had to use the Kelvin temperature, because the Kelvin temperature is directly related to the average kinetic energy. Not the Celsius temperature or the Fahrenheit temperature. The Kelvin temperature is directly related to the average kinetic energy. So when we talk about molecules moving around, and again, we just finished the unit on gases. When we talk about molecules moving around, we talk about their average kinetic energy, because all of the molecules aren't moving at exactly the same amount and same speed, so we take an average of that. And when we talk about the Kelvin temperature, it's directly related to that average kinetic energy. No negatives, no zeros. We have absolute zero there, which we can never reach. So we can refer to that and say, well, here's the temperature, and that's related to how quickly those molecules are moving in that. Besides kinetic energy, we also have another major type of energy, and that's potential energy. So if you go back up to the teak, we have kinetic energy, and within that we can talk about thermal energy. Here we have potential energy, and within that we can talk about chemical energy. So potential energy, or PE, is actually stored energy. So if we compare these two, we have kinetic energy, which is energy of motion, things are moving, and then we have potential energy, which means we've stored that energy so that we have that ability to do work when we want to get to it. So potential energy is that stored energy. And there are lots of types of potential energy. The most common type that we think of is gravitational potential energy. So if something is set up high, it's not actively moving, but if you can, really the only thing that keeps it back or keeps it from moving is some type of friction, or somebody's holding it on there or something like that. But it's got the ability, because if you get it close enough to start it moving, give it a little bit of activation energy, all of a sudden gravity is going to pull it back down. It's going to move a lot more. So potential energy, gravitational potential energy, is a really common one. What we don't think of, or probably what you haven't studied before, is the chemical potential energy. And so within that, just like we have thermal energy that hooks up to kinetic energy, here we have chemical energy, which is a form of potential energy. And sometimes, instead of calling this chemical energy, they call it bond energy. Or in many cases, instead of talking about energy or being more specific when they talk about it, they call it bond enthalpy, or the bond heat that's associated with that. If you decide to take AP Chemistry, then we'll talk more in terms of enthalpy. It's just a very specific type of energy. Energy is the ability to do work, if we go back up here, but there are lots of different types of energy. We say kinetic energy and potential energy, but even within those, we can break it down into smaller or more common aspects. Like we have electrical energy and heat energy and light energy and sound energy. So when we talk about kinetic energy, well, sound energy is a form of kinetic energy. Sound vibrates the molecules. It causes them to move faster. So we can put those other forms of energy into this. When we talk about heat energy, heat can actually move the molecules around, and we can call that, once they're moving, we call that kinetic energy. So there are lots of different ways that we can talk about this. So we have kinetic energy, and within that we can talk about thermal energy. We have potential energy, and within that we can talk about chemical energy or bond energy. And there are various ways that you can see these written. A lot of times we'll have TE for thermal energy, or we'll have enthalpy, another word for that, or delta H, a change in heat, a change in thermal energy. So you'll see these in a lot of different ways. But when we talk about this chemical energy, there are two pieces of info that you really, really need to know. And first and foremost, when we talk about chemical energy and we talk about it being potential energy, stored energy, where is it stored? So in this case, this stored energy, where is it stored? It's stored in the bonds. The bonds between atoms. You know, we talked about ionic bonds and covalent bonds. So this energy is stored in the bonds between atoms. That's where that energy is stored. So if we can break those bonds, we can, or we can make those bonds, making and breaking bonds, then we can have access to that energy. So there are two major other pieces of information. When we break bonds, it requires energy. So breaking bonds requires energy. And when kind of a way to keep this straight in your head, I want you to think magnets. It's not a perfect example of this, but it kind of gives you an idea, kind of gets it straight in your head. Think of magnets. You have to really put energy into it to pull those magnets apart. The other thing is that making bonds releases energy. Okay, so if we're thinking this in terms of magnets, again, it's a loose analogy. When we break those two magnets apart that are stuck together, it requires some energy to be put into it. And yet when you put those two magnets, you get them close enough together, all of a sudden you don't even need to put energy in it, it sucks it in together here. So that's kind of a way just to remember, hey, breaking bonds requires energy, making bonds releases energy. But again, there's even more to it than that. So just keep me in mind, keep things in mind. So when we have these breaking bonds requires energy and making bonds releases energy, in general, this is what we're dealing with. So we know that when we have two chemicals or two atoms that react together, we produce a product. So in general, for the most part, when we have these two reactants, we are creating bonds between them. We're making bonds between them. And so when you have a product that's formed, what you get is something that has released energy. It's more stable, and nature favors a lower potential energy. So this reactant had higher potential energy, and this reactant had higher potential energy. And when you got them together, they had a lesser potential energy. They were more stable that way. That's why a lot of times you can't find pure elements in nature, because they're unstable in that form. And when they form compounds, they're much more stable. They don't react very easily when we have that. Now, within this section, I'm going to give you a little bit of an AP connection. And really it's talking about the terms here. And one of the first terms is we talk about delta H. And this equation that I'm about to give you, I'll explain it here in just a minute. Delta H, and it's going to look ugly. We have the summation of the bonds broken minus the summation of the bonds formed. You know, we can't just put this black and white statement and say, hey, every single time all of these bonds breaking requires energy, and bonds making bonds releases energy. There are always gray areas in chemistry, and so we can't just automatically say that every single reaction that's a synthesis reaction is going to be releasing energy, and every single reaction that's a decomposition will be taking in energy. We can't always do that because, of course, chemistry has to have all these gray areas here. But we can calculate it every time. And so somebody else has done all the experiments for us on calculating how much energy is released when this bond is broken and how much energy is taken when this bond is formed. So there are charts all over the place. So when we can look at a chemical reaction, we can draw out all the molecules of the reactants and the products, and then we can go through and add up all the energies and end up subtracting them and figuring out what heat is either absorbed or released. So the first thing I want to point out here is this thing right here. Delta H is enthalpy. Weird word, enthalpy. Enthalpy is the heat associated with a chemical reaction. Okay, so when we talk about energy with a chemical reaction, we can say in the big picture, we can talk about it being thermochemistry or thermal energy, things like that. But really what we discuss it as is enthalpy. So we want to talk about the change delta. We've had that little symbol before, delta, the change in temperature. So the change in enthalpy. How do we know? Is energy going to be taken in by this reaction, or is energy going to be given off by this reaction? And how much energy is going to be taken in or given off? There are a couple of other terms that we want to put in here too. And the first one is delta G, or the next one I should say, delta G, and this is Gibbs free energy. And it sounds like, somebody's got a sale or they're giving stuff away here, but in reality they're not. What they're talking about is how much energy is available to do work. Free energy. How much energy do you free up to do work? How much energy is available to do work? Okay? And we use this to determine whether or not a reaction is spontaneous. Will this reaction happen on its own? This is a big thing in the AP chemistry. And instead of saying spontaneous, they've decided to come up with a different phrase for it, which is really a mouthful, and they call it thermodynamically favorable. And then the last term that I'm going to give you here is delta S. And delta S is the change in entropy. And entropy we can think of as disorder or chaos. One of the laws of thermodynamics is the entropy of the universe is increasing. That's just a natural thing. The chaos, the disorder is increasing. Things are running down. And that's just something that in reality. You use something over and over and over again and it wears out. That's the law of entropy. I can't remember which number of the law it is, but we have entropy. So we end up having delta H, delta G, and delta S. And all of this is concerned with energy associated with chemical reactions. So when we come back up here to the top, we can see this thermochemistry unit 12 over here. All of this is dealing with energy associated with chemical reactions.